Okay. Okay, so first of all, the few things I want to address when I noticed some issue when I grade the homework 1, for example. So, oh, by the way, I noticed that my microphone might have some issue like from last week. I think it gets fixed now. But if you, in the middle of the lecture, if you notice that the microphone doesn't work, like you cannot hear me, or actually the sound, suddenly the quality actually change, please let me know right away, because I'm keeping eyes on the microphone, but I just hope that it doesn't break down in the middle. So for homework 1, when I graded the homework, I'm halfway through, so I noticed that there's a certain issue I want to address. So most of people did it okay. Like some of the common issue is essentially that people didn't justify each step. So sometimes that you might think that it's obvious, but the thing is that like the whole point of this course is not just to get the right answer. It's actually the process is more important than the final answer. So I especially would emphasize on like you need to justify each step. Like for example, why a statement is true, right? It's based on certain proposition we're going to use. So because this is homework, so I'm going to put a higher standard in the sense that you have all the resource like the textbook with you that you can actually check why a statement is true in general. And another thing is that actually I noticed that maybe 2 or 3 people did the wrong question. So be careful that because I'm assigning the question from the textbook. So I actually saw that like some of the students that, for example, like did, for example, instead of doing number 11, like they do number 12, for example, or actually draw the wrong picture. And actually the picture is very important, right? You need to get the picture correct. But do not rely on the picture very much in the sense that because certain problems, like for example, I'm going to talk about like the homework number 4 from last time in a minute. So you're going to see that the certain situation, like even the angle looks like half of certain angle. It doesn't necessarily be half of it, right? So sometimes the picture can be misleading. You need to be really careful about that. So don't do the wrong question. This time I give like people who did wrong question, I think I give it, for that problem, I give 1.5 or 2 points, something like that out of 5. But in general, in the future, I'm going to grade even harsher. If you do the wrong problem, most of the time I'm going to give 0 because I cannot grade it, right? This is not the problem I assigned, okay? So please just be careful, double check whether you do the correct question. And another thing that I noticed is that if you want to, so most of the time, I'm going to assign the question where you only need to use the things that we already covered, for example, in the textbook or in the lecture notes. So when you want to use something that's outside the frame, for example, when we talk about, say, around proposition 1.20, if you want to use proposition, say, 1.40, sometimes there might be an issue because you're using something, first, logically, it's not correct in the sense that you're using something we haven't justified, right? Second, another thing I would worry is that logically, you might get something called loop logic, right? How do you know that the theorem or the statement or things that you quote does not depend on the things that you are proving? That's the thing you need to be very careful. So usually I don't recommend using something outside what we are covering right now. And if you really think that, oh, in the last minute, you cannot think of any other way, you just see some resource or some theorem, then make sure you cite it. Like for example, if you see someone cite like some author resource, you should definitely cite it and tell me which thing you use. And a lot of time, you can notice that I give you some hints from the homework, and that's pretty much, I would say, the easiest way to prove it, right? So if you need to use an outside resource to prove this, then maybe that means you don't really understand the concept that we teach here, because then you essentially are doing a detour here. So when you use an outside like resource or theorem, make sure you really do it correctly. And this happened in the past that some of the students that would directly use the copy, for example, copy the answer from like, I don't know, some online forum or something like that. And then because I'm the one that who's grading the homework, so I can definitely tell whether this is something like usual or unusual, because I could tell that whether you understand what you're writing or not. So I understand that some of the question can be hard, that maybe you're going to use some online resource as a reference. Then if you really did that, technically you should actually cite it. For example, you say, oh, I saw this or that online. You need to tell me what's the resource. This is the correct way of doing like academic homework, for example, right? Like otherwise, if you don't cite it and you just directly copy it as if that's your own answer, then that's actually plagiarism. And this can be very serious. So if you really use outside resource, you should definitely cite it and tell me where you get it. Okay, so that's one thing. And don't forget that homework 2 is due on Wednesday. I already write it down for you. And then another thing is that please read section. So after, we're going to finish 3.3 today. And after this, what we're going to do next on Wednesday and also next Wednesday is that I'm going to talk about Hilbert's axiomatic system. So in this case, like I would highly recommend everyone read in advance from section 6.1 to 6.3 for Wednesday's class and also next Wednesday. So I'm going to use the slides to talk about all these things, and then just a lot of things that you need to read. So if you don't read in advance, that it's very highly possible that you're not going to catch up for the next 2 classes. So especially for Wednesday and next Wednesday's class, please read in advance for the first 3 sections from chapter 6. So we are going to skip chapter 4 and 5, and we will come back to it at the end. Okay, so as I said, what I'm going to do, I want to just briefly use like 3 minutes to quickly talk about one of the problems from homework 1. So let me write it here. I will include it with the notes later on when I post it. So this is essentially homework 4. Okay, so I want to point out some common issue and also go over this problem. So this is some common issue I saw. So for example, I believe the problem tells you that this is an isosceles triangle with AB equals AC, that's given. And also they tell you that pick D and E on AB and AC such that AD equals AE. So I still see a lot of, not a lot, but I still see some of the people actually treat this problem as a construction. That's not correct. This is not a construction problem, okay? So I remember I mentioned this last time, but still some of you still like maybe forget about it or didn't pay attention about this problem. This is not a construction problem. Namely, all this condition here that you saw, AB equals AC or AD equals AE, this is our given. You don't need to construct it, okay? So what are you going to do here? Then they ask you to draw the picture, meaning just draw a indication picture. So you have a triangle A, B, and C. And this D and E points can be chosen arbitrarily, right? So it shouldn't depend on where you pick D and E, as long as D and E satisfy the fact that AD equals AE. So these 2 conditions are given. They're not constructed. They're essentially given as an assumption. Okay. So now the thing is that you need to use this assumption, and I want to prove that CD equals BE. Okay. So let me use different colors. So CD equals BE. So first you need to get this picture correct. That's why the question asks you to draw the picture, because they want you to make sure, that you really draw a correct indication picture. So I noticed that some of the, like 1 or 2 students that actually got the picture wrong. If you got the picture wrong, then of course you're going to prove the wrong thing. So actually point D is on AB and point E is on AC. That's one thing you need to be careful. So in order to do this problem, you need to use all the condition, all the assumption that's given, right? So basically first we know AB equals AC, and also we know AD equals AE. So the first thing, there's several ways of doing this problem using SAS congruent scheme. So I'm going to just do probably the way that I saw most people did it, is that, so first of all, you have these two conditions. I'm not going to write a complete sentence because I want to do it quick. So what you can do is that you observe that BD is essentially AB minus AD, right? But AB is the same as AC, and AD is the same as AE. So this tells you that BD essentially is the same as CE. Okay, so that's the first extra information we can get. And also, since triangle ABC is isosceles triangle, right, with AB equals AC, so we know by proposition 1.5 that the base angle should be the same. So one common mistake I saw here is that either people didn't justify that why this is true, right? So I want to see that you really know it comes from 1.5. And second, keep in mind that the definition of isosceles triangle is a triangle with a pair of equal sides. The original Euclid's definition has nothing to do with the angle, okay? It's essentially that you prove in 1.5 that if you have isosceles triangle, meaning if you have a triangle with a pair of equal sides, then you can prove the base angle of that triangle is equal. So this essentially, this conclusion is not from the definition, it's from 1.5. Okay, so you need to get the logic correct here. So now we have this second condition. And if you notice that BC is a common side of two triangles. So either, so you want to compare BCD and CBE, right? So if you compare these two triangles, let me draw the picture here, right? And EBC, right? And we already know this angle is the same, right? And we know DB is the same as EC, and we have a common side here. So essentially you have the picture like this. Right? So this essentially tells you you have SAS. So by SAS scheme, from the SAS scheme, the conclusion you can actually get first, you should say that after the congruent scheme, you first get the conclusion that the triangle BCD is congruent to triangle CBE, right? That's the first conclusion. Then, because the two triangles are uncongruent, so the corresponding sides should be equal. So it tells us that, so then CD is going to be the same as BE. So a lot of people actually skip the congruent triangle step, right? This is not correct, because by the congruent scheme, the first thing you get is actually two triangles are congruent. So you get the conclusion that those two corresponding sides are equal. So this is essentially how you do the problem 4 in that homework 1. So I see several common mistakes, so I just want to point it out and clear the thought. So if I'm going to finish the grading hopefully by tomorrow, so definitely by before the Wednesday's class. So I'm going to re-upload it as a file. So it turns out that the Blackboard system is not easy for me to directly grade it on this. So I need to actually download all the file and re-upload it. So later on, you will see that in the re-uploaded files that I give to you as an attachment in the comment, you're going to see that I make a lot of remarks. So if you later on, if you see like you get, for example, for each question, I think each question is 5 points. If you get say below 2 points for that problem, then you need to definitely check with my solution later on, and then also come back to ask me to figure out how to do this problem. Okay, so before we get started, is there any question for this problem I just mentioned? So I want to make sure everyone know how to do this problem, this type of problem essentially. Okay, so I'm going to go back to what we left off last time. So I'm going to include this page with the notes later on. Okay, so what we're going to do, as I said, it's a remaining things for the section 3.3. And as you probably remember from last week that I left with some proposition from 1.20 and 22, something like that. So what I'm going to do is that I want to cover everything related to parallel lines. And then after that, I will come back to proposition 1.20 and then some of the things I left, because I want to keep the construction at the very end. So first, before we can do that, I need to recall some of the definition that we did, we talked about last time. So let's say if you have two parallel lines, right, or two lines, and crossed by a transversal, right, EF. So we usually call like a line crossing two lines transversal. And last time we talked about all this like terminology, interior angle, exterior angle, right? So interior side, let me remind you, is this side, right? So you have 1476, that's essentially the interior angle. And everything outside like will be exterior angle. And you also have some terminology for alternate interior angle or alternate exterior angle. Okay, so this is something that you need to be a bit careful. You need to know this, because otherwise some of the later proposition may not make sense to you, because if you see this terminology and you don't know what that means. So, so that's just go to proposition 1.27. So this is essentially exactly what I asked everyone to prove in homework 2. So if you haven't do it, then I'm not going to tell you exactly what to do, but since this is included in the homework 2, but I'm just going to remind you what the statement is here. So first of all, this is actually the very first proposition that's kind of related to parallel lines. So if you have two lines, L and M, like this, and you have a transversal crossing these two lines, L and M, and if these two angles are equal, for example, either number 1 equals number 2, or you can say if alpha equals beta, and this pair is what we call, exactly what we saw, it's what we call the alternate interior angle. So this tells you if the alternate interior angle, either one of the pair, are equal to each other, then right away we have the fact that this implies that the line L is parallel to line M. And you're going to see later on, I'm going to use this notation for convenience. Okay, so if you already read this part, or if you already did the homework, then you probably already knew that like the proof is essentially proof by contradiction. And also we are going to use the exterior angle theorem. So let me remind you, exterior angle means that, yeah, this is the one that we are going to rephrase. That's the 1.27 in the homework 2. Okay, so the rough idea is that, so you want to prove L is parallel to M, right? That's your conclusion. So what they did, roughly speaking, is that they do proof by contradiction, right? So they still assume either angle 1 equals angle 2 or alpha equals beta, but they say, oh, what if L is intersect with M at some point, right? And they form this triangle that I draw here. And then they're going to use the argument trying to see what's the information we have, plus using exterior angle theorem. And so what's exterior angle theorem? Let me remind you, it essentially tells you that if you have exterior angle of a triangle, then that exterior angle should always be strictly bigger than either one of the interior angle inside of the triangle. So by assuming essentially the contradiction, assuming that the conclusion is not true, you're going to eventually have a contradiction. If I remember correctly, it's going to contradict the exterior angle theorem. Okay, so that's essentially the rough idea of this proof. And please, you should definitely, or I hope everyone already started the homework 2. So you have, so I would, if later on I will come back to talk about this if I notice that everyone has an issue with proving this problem. Okay, but for now, that's going to just use this proposition 1.27. So basically, we see if we have equal alternate interior angle, then two lines are going to be parallel. Okay, that's the conclusion for 1.27. And for the next couple things, especially proposition 1.28, it's a direct application. it's actually super easy if we have 1.27. Okay, that's why I say it's application for 1.27. So the statement is the following. So there are two parts for 1.28. First part is that if angle 1 in the picture is equal to angle 3, then it says that these two lines, L and M, are going to be equal. Okay, and similarly, if you have angle 1 plus angle 2 to be double of the right angle, meaning essentially 180 degrees, then we also have the same conclusion where both lines are parallel. Okay, so what's this 1 and 2? Usually we call this 1 and 2 alternate interior angle on the same side. Interior on the same side. So they're interior angle on the same side. So sometimes you will see that in the textbook or later on in other literature, they might call angle 1 and angle 2 to be interior angles on the same side. So if the sum of 1 and 2 are 180 degrees or double of the right angle, then we know that this is going to be parallel lines. So to prove this, I actually want to prove this because it's actually very straightforward if we directly use the 1.27. So I'm going to start from proving proof of 1, the statement 1. And I'm going to prove 2, and you're going to see that this are pretty similar. Okay, so first of all, so we know 1 equals 3, right? Angle 1 equals 3. And I'm going to call this angle 4 here. This is my tool here. Okay, so first, since angle 4 and angle 3 and 4, sorry, are vertical angle, right? Remember that if they're essentially opposite of each other in this case, this is what we call the vertical angles. Since they're vertical angles, so let me remind you, this is essentially the statement from 1.15, the vertical angle theorem, okay? That if we have vertical angle, then they are equal, right? We kind of already know that, right? This is kind of like self-evident in some sense, okay? Now, we know, because now we know angle 1 equals angle 3, right? So we already know angle 1 equals angle 3, but at the same time, 3 and 4 are vertical angles, so they're equal. So right away, we get the fact that angle 1 equals angle 4, right? So basically, this tells us what's angle 1 and angle 4. You can see that this is another pair of alternate interior angles, right? So essentially, we got the alternate interior angles are equal. So the alternate interior angles are equal. If this is the case, then essentially we have the assumption. We can use the 1.27. So this is essentially telling us by the proposition 27 that we just saw, then we essentially get that L is parallel to M. Okay, so you can see that the whole goal is to be able to get the condition that the alternate interior angles are equal. Once you have that by 27, proposition 27, right away it implies two lines are parallel. Okay, so the second statement is also similar taste, right? So I'm going to prove the second one as well.
I have a question.
Yeah, sure.
So it says, where you say that is the alternate interior angles are equal, is that our justification for if angle 1 equals angle 3, then angle 1 equals angle 4?
Oh, no. So that's not a justification. The justification that this is after that. So this is the alternate angle is 1 and 4. So I'm just restating that so first you have angle 1 equals angle 3. That's the assumption, right? And by proposition 1.15, we know 3 and 4 are vertical angles, so they're equal. So using the fact that 3 equals 4 and 1 equals 3, we got 1 equals 4. 1 equals 4 is the same as alternate. They're alternate interior angles. So that's why it's the same thing as having equal alternate interior angles. Yeah.
Okay, thank you.
Yeah. Okay, so now for 2, we have the same philosophy. We want to get, once we can get to alternate interior angles being equal, then we're done, because then we can use 1.27 to imply that L is parallel to M. So how do we get to that step when we have the assumption where 1 plus 2 is 180 degrees, right? So we know that first, since angle 2 and angle 4 from this picture are adjacent, or essentially you can say supplementary angle, right? Then essentially this is something we also saw before by proposition 1.13, that if you're having supplementary angle, oops, this is 4, not 14. The sum is going to be 180 degrees. So I'm being a little bit sloppy here. I should probably write double of right angle, but I want to be quick, so I just directly write 180 degrees. However, we also know, we assume 1 plus 2 is already 180, right? So this tells us that, okay, then number 4 is 180 minus 2, right? But at the same time, 180 minus angle 2 is the same as angle 1. So this again tells me I have equal alternate interior angle. So basically, again, by proposition 1.27, since we have equal alternate interior angle, then by this previous proposition, we know that L is going to be parallel to M. So you can see that, okay, we need to use a little bit other proposition, but the key point is to use proposition 1.27. So that's why I really think 1.27 is quite important. That's why I'd rather people spend some time to read it. If I just prove it for you, probably people will not go back to read it again. So I want people to really try their best to rephrase and give an update proof. So in that case, you will really, so why can we assume this is what I want to prove? I want to prove that if I assume 1 plus 2 equals 180, and I want to prove that it implies L is parallel to M. That's the assumption it's given. That's the statement I want to prove. Yeah, so that's why I can assume. Yeah. Okay, so now, so this is actually quite straightforward. So I'm going a little bit fast, and probably because it's on the screen, so it's probably hard to process. But believe me, once you have 1.27, you can probably just read the 1.28 by yourself. It's not that hard. It's really just this much. Okay, so the textbook might write redundant, as probably you already know by now. If you already read the textbook, you can see that Euclid's original proof was very long and redundant. But that's how his style back then when they're trying to read to write a very rigorous proof. But if you really use your own modern language to rephrase it, to write an update proof, it's really just this short, okay? So another thing I want to do before we move to the construction is that, this now I'm going back to 1.20, okay? So for the next, after this 1.20, the next couple construction, I'm going to use, it's going to relate it to this triangle inequality theorem. So first of all, you probably already heard about this or saw this before, that this is essentially kind of a famous fact, or an obvious fact that we already know. But it turns out that surprisingly, this is something that we know we should prove, right? A lot of actually straightforward theorem or well-known statement, it's actually not that easy to prove, okay? And you need to actually prove it. So the triangle inequality theorem tells you that for any triangle, if you have the sum of any two sides should be greater than the third side. Okay, so if you have this triangle A, B, and C that I draw here, then this essentially tells you either you're going to have A plus B bigger than bigger than C, and also A plus C should be bigger than B, and also B plus C should be bigger than A. Okay, these three should automatically true if you have a legit triangle. So in some sense, like if you're a math major, you probably heard this before. It means that these three things I just wrote down is the necessary condition for having a triangle. Okay, if you want to be able to form a triangle, right, then it means that these three conditions need to be satisfied. Okay, and I'm going to call the first one case 1, case 2. So we have several cases. So technically, if you want to rigorously, completely prove this 1.20, you should prove case 1, 2, and 3, right? But here, for the time being, I only have time to do the case 1, essentially, one of the case. But you should be able to do the other 2 cases because they're actually the same philosophy, same steps. You just need to kind of swap the role of some of the vertices or the sides here. So I think one of the homework I'm going to assign for this coming week is to do or to finish the other 2 cases for this proposition. But I'm going to show you one of the case, and you can also see the textbook for one of the case, the proof for the one of the case. Okay, so this actually, the result seems easy or seems like well-known, but the proof actually needs a little bit trick here. So that's why I want to go over this this proposition. So we're going to only prove 1 cases. And so first, let's say we have this picture, the triangle A, B, and C that I draw here. So I want to prove that AB, the side AB plus AC. Okay, let me go back. Plus AC is going to be bigger than the third side. Okay. So now first, let's see how are we going to do it. So the first step, I'm going to do, I'm going to extend the segment BA to a point such that DA is going to be equal to CA. Okay, so what does that mean? It means, okay, I'm going to extend BA in a way that long enough that it reached to the point D such that DA is the same as AC. So this is doable, right? Because this is essentially by postulate, the axiom, postulate 2, that we can always extend a straight line indefinitely to whatever length we want, right? Okay, so that's the first step. You can see that we need to do this kind of trick here. After this, then we joined the CD. Okay, so let's join CD here. Okay, so now I have this another triangle I can work with. Okay, so if this is the case, you can see that this triangle AC and D, right? Because AC equals AD, so this is an isosceles triangle. So right away, you can see by proposition 1.5 that we learned before that the base angle of isosceles triangle is going to be equal. So by proposition 1.5, we know that angle ACD is going to be the same as angle ADC. Okay, these are the 2 base angles. Okay, now what information we have here? So now I'm looking at another bigger angle here. So let me draw the picture here. So I want to say, I want to use this bigger angle here, angle BCD. Okay. So since we know from this picture, right, angle BCD essentially contains the angle we just see, like angle ACD. So we know BCD is bigger than ACD, right? From the picture, it's obvious because it's bigger, right? So what does that mean? But we know ACD from here is the same as ADC, right? So this automatically tells us that BCD is also bigger than ADC. right? So this means this BCD here is bigger than the angle at ADC. Okay, so you might wonder, okay, what's going on here? Like we things go very further, right? So the reason that we want to have this comparison of the angle is that later on we are going to use this very useful proposition that we actually saw before. So I'm going to come back to the triangle here. So I'm going to use or focus on the triangle BCD. So in triangle BCD, by this proposition 1.19, so let me remind you what's 1.19. So 1.19 tells you if you within a triangle, the bigger angle should corresponding to a bigger opposite side, right? And vice versa as well. Vice versa is the other proposition. But 1.19 tells you if in a triangle you have a bigger angle, then the opposite side should also be bigger. The corresponding side should also be bigger, right? So if you see that in triangle BCD, we already know that this angle BCD is bigger than ADC, right? So that means the corresponding side of angle BCD, which is the side BD, should also be bigger than the corresponding side for angle D. So this is essentially obtained from 1.19. Okay, so we know, maybe let me add a remark. So BD bigger than BC because BD correspond to bigger angle. Maybe this is more clear, okay? Now we are almost done because now we have this nice correlation between sides. So now, but we also notice what's BD here. BD can be decomposed from the picture. It becomes BA plus AD. Okay, so keep the BA. But at the same time, remember, we know that AD is constructed or essentially chosen that AD is the same as AC, right? That's from the very beginning. And so then basically we can see what's going on, right? So you have BD and BA plus AC. Right, so let's see. And we also have another thing from here. Let me copy down. But just from the last line, we know that BD is bigger than BC, right? But we also know BD is the same as BA plus AC. So in the end, we are done. So we know BA plus AC is bigger than BC. And this is exactly what we want to prove at the beginning. This is essentially the triangle inequality theorem. Okay, so you can see that. Okay, I'm explaining it like quite slow because I want to make like provide enough detail. But as you can see, this is also not like, I wouldn't say it's very difficult. Like it's quite straightforward. But at the same time, that you need this kind of extra trick to help you, like for example, draw an extension line and all that. So I just want to mention this so everyone can appreciate that a lot of like theorem, for example, like a well-known theorem or maybe easy theorem that we thought in say Euclidean geometry or high school geometry, turns out it's not really that straightforward to prove in some sense, right? You need to prove it and we can prove it. So as I mentioned, the remaining two cases, right? So you can do, here I proved BA plus AC is bigger than BC. You need to prove two other cases, okay? So this works because we can construct as a, yeah, so postulate 2 tells you can, so it's, postulate 2 doesn't say anything about isosceles, but what happened is that postulate 2 tells you that you can extend a line indefinitely. So you can extend a segment along the same direction or opposite direction to any distance you want. So that because of this postulate, it allows us to extend BA to any distance we want. That's why we can construct this AD such that it has the same distance as AC. Yeah, okay. Okay, so this is 1.20. So the next thing I want to do is directly related to this triangle theorem. So let's go back to the statement. So the triangle inequality theorem says if you want to have a if you have a triangle here, right, a legit form triangle, then the sum of any two sides should be bigger than the third side. Okay, so this tells us that if you want to form a triangle, this has to be true, right? This theorem has to be true. So the other way around, kind of like a converse of it, right? If I want to give you three segments, right, and I say, okay, use these three segments with certain lengths to draw me a triangle, then the first thing before you can even draw it, you should ask me whether these three segments satisfy this triangle inequality, right? If it's not, then you won't be able to draw a proper triangle at all, right? You probably can imagine that sometimes if two sides are too small, then you cannot close it up. You're not going to see a triangle. So this means in order to form a triangle, right, your three sides need to satisfy this triangle inequality theorem. That's the first thing you need to satisfy. So the next thing I'm going to do is essentially to show you, essentially this is a construction that I give you give you three segments which satisfy this like this assumption, basically A plus B bigger than C, A plus C bigger than B, B plus C bigger than A. If my three segments satisfy these conditions, then I can use the construction to draw a corresponding triangle with the given side. Okay, so this is what we're going to do here. Okay, so first of all, let me give me a second. I want to turn off this. So let's see. Okay, I want to stop share new things. Okay, so everyone should be able to see the dark camera here. Okay, so now let me see. Okay, so the first thing, as I said, I want to prove is that if I have three segments, if given three segments, I want to, and then like what I said, this three segments, in order to draw the triangle, it needs to satisfy this condition here, right? Because essentially this is the necessary condition in order to have a triangle, okay? If this is correct, right, this needs to be correct at the first, then we can construct a triangle such that the three sides is equal to the given three segment here, okay? So unfortunately, I mean, because if I want to really do a super rigorous proof, it's going to be like taking too much space and time. So I'm going to tell you in a minute that there's a certain step I'm going to skip, okay? So this is not the very rigorous, the most rigorous construction picture. But I just want to show you at least what's the construction steps. And say if I really want to test you, for example, either in the exam or something, I would explicitly tell you that which steps you can omit, especially if I'm going to test you this 1.22. Okay, so first of all, let's see, how am I going to construct this, right? So let's say I was given three segments A, B, and C, right? You can call any of them A, B, and C. Doesn't matter which one is A or B. Then the first thing you need to do is you draw a straight line, DE. And you want to construct on this straight line, you want to pick out few points F, G, and H, such that I want DF to be A, FG to be B, GH to be C. So I want DF to be A, FG to be B, and GH to be C, the length, okay? And this can be done by proposition 1.3. So let me recall what's 1.3. 1.3 says if you have a longer line and a smaller line, you can actually cut off the smaller distance, right, from the longer line. But as you can imagine, if I want to repeat the whole step by 1.3, it takes me another 5 to 10 minutes to do it. So that's why what I'm going to do is that I essentially omit some steps. So I want to make a remark here. I omit the sketch of 1.3. So I omit these steps here. So that's why you already see that I put it out on, I put a sketch on the picture here. So so from now on, let's just assume DF is equal to the A segment given, and FG is equal to the B, and GH is equal to the third segment I want here. Okay, from here, everything will be much easier. Otherwise, I need to actually spend another 10 minutes just to do the construction one here. But so, okay, so once you have everything like cut it off from the longer line DE, then the rest of it is actually super straightforward, and it only needs like probably, I would say technically 1 steps. Okay, so first thing you want to, first thing, construct a circle center at F with radius FD. Okay, and you construct another one. Okay, so FD. Okay. Okay, so first you take a circle at center at F and with radius FD. And you do another one center at G, but with the smaller radius GH. Oops. Okay, so now you can see that they intersect at roughly here. Sorry, the picture is not very clear, right? So the 2 circles intersect at point that's called it, I call it K. Okay, now third step, I'm going to join KF and KG. KF and KG, right? Then I claim that this triangle K, F, and G is the one I want. So this small tiny triangle that you saw here has the required length that I want. Okay, so basically you can see really just directly from the construction, you pretty much can right away see why this is true, right? So actually I can go over the verification, but you can actually kind of imagine that this is kind of pretty obvious to see, right? So first, let's just go over what we did, right? So you draw a circle center at F, right, with radius DF, and you intersect at K, right? So this tells you that DF and FK is going to be the radius of the same circle, right? So we know by definition, DF equals FK. So right away, you know that this FK should be same as A, right? Because DF equals A. And another thing is that, so let me put it here. And we do the same thing. GH is the radius, and also GK is the radius of the smaller circle, right? So by definition, we have GH equals GK, right? So that means right away we have a C here, right? So, and what about FG? FG is already kind of seated there because we constructed to be the same as B, right? So let me pull out bigger picture here. So essentially you are looking at a triangle like this, right? So that's why I can directly say that the triangle FGK has the given side, right? Because we already require DF, FG, and GH to be the length that we want. That's from essentially the construction of first step. Okay, so the verification is kind of pretty straightforward directly from the picture here. So as I said, I kind of being a little bit sloppy and cheating here that I didn't do the construction one. But as you can imagine, if I already give you 3 segments lining up like this on a straight line, and I ask you to use those three segments to construct a triangle, then it can be done in, I would say, 5 minutes, right? If you do it quick. So it's not very difficult, but you can imagine that you can try, right? If you pick up the length or segment A, B, and C not careful enough in the sense that it doesn't satisfy this inequality, then you can see that the two circles may not intersect. Then that's where the construction fail, right? So you can imagine that in some sense, this construction works because the three segments you start with satisfy the necessary condition we need. Okay, so that's why 1.22 is highly related, tied up with the triangle inequality theorem we just saw, right? Because in order to construct a legit triangle, right, you need the three sides to first satisfy this inequality. Okay, is there any question so far? Okay, so now the next thing I want to do, so the next couple thing is all kind of based on this. So probably you already see that one of the drawback, which one of the things I personally don't like that much, is that you see a lot of Euclid's construction proof relies on the previous construction, right? Like what we did here. So it's not the most efficient way to do it, even though logically it's rigorous, right? If you think about it, because essentially the style of Euclid's element is that he only used the proposition that was already proved, right? And that will help him to build on the result later on. But it may not be the most straightforward proof, right? Because he need to keep quoting a previous order construction here. But by no means, like Euclid's construction proof here is not the only way to do it. You can definitely come up with other methods that does not rely on a previous proposition. Some of them you can come up with 2 or 3 different type of proof. Okay, so I just want to remind you that like Euclid's way may not be the best way to do it. So another thing I want to do, which is essentially a direct application of constructing a given constructing a triangle, is the following. So I'm just going to talk about it because I'm not going to prove this. We don't have that much time, but I'm going to tell you what's the ideas of the proof. So essentially 1.23 tells you if you are given an angle, whatever how big that angle is, let's call it alpha, okay? And you're given a segment or a line, right? A segment AB. Then this construction allows you to reproduce angle alpha on the line AB. So you are able to construct or essentially duplicate angle alpha on the segment AB. And so essentially you can create an angle CAB such that it's going to be the same as alpha. Okay, so you might wonder why this is related to triangle, right? I'm doing an angle, just one angle here. Why I can say this is an application of 1.22. So I'm going to draw the picture. Let me see whether I can just, probably I have some space here. Let me draw a picture here. Idea for 1.23. Okay. So the idea, essentially, I'm just going to talk about the idea of how they do the construction. So you say, okay, you have an angle here, right? Let's call it alpha. Okay. And let's give it some other name. Let's call it, I already used A, B, and C. So let's do EFG, right? Doesn't matter. Okay. So I say, okay, I have this angle. I want to reproduce the same angle on this segment AB, right? So the straightforward idea in some sense, if we want to use 1.22 is that, okay, then I just connect these 2 points on the angle alpha. Doesn't matter how long it is, as long as I can form the triangle EFG, okay? Then the idea is you are going to duplicate triangle EFG on AB. That's the idea. So what you're going to do is that essentially you hope that you can pick out EF here. Oops, sorry. Right? You can pick out some points here and another points here. right? That's coded AC, I round up ACG, right? If you can duplicate triangle by using 1.22 above, right, which we can do it, right? Because you already have the given 3 sides, right? So that's coded 1 bar, 2 bar, and 3 bar, right? Then what you can do is essentially reproduce a triangle with the same length like this, right? Then automatically you're going to have an alpha here. That's essentially the idea of this construction using 1.22. So that's why I kind of don't want to redo it again, because this is essentially the key philosophy behind the construction. But it takes actually a while to rigorously do all the steps here. So I just want to kind of tell you that you can use the fact that we can construct a triangle from a given length, and to use this to construct any angle you want. Okay. Is there any question so far? Okay, so the last thing I want to do is, let me put it back here, is this proposition. Okay, so you can see that there's a jump of proposition. So I think last thing we did just now was up to 1.28. So you might wonder where is 29 and 30. So unfortunately, 29 and, so remember when we talk about chapter 3, we only want to introduce any proposition or theorem that only depends on the first 4 postulates, right? Remember, 5th postulate is the controversial one, right? So anything that only depends on the first 4 postulate is what we call the neutral geometry. And it's going to hold for any geometric model, okay? So that's why the main goal of chapter 3 is essentially to talk about anything that's within the scope of neutral geometry, meaning we only want to first look at those propositions that only depends on first 4 postulates. So unfortunately, proposition 29 and 30 would depend on the 5th postulate. That's why we want to delay it to later on. So that's why you can see that if you read the textbook, there's a jump till 1.31, okay? So 1.31 still does not depend on 5th postulate, so we are safe. So 1.31 says now it's related to parallel lines. So through a given point, I want to draw a straight line parallel to another given straight line. So that means given a point outside the line, right? So I have a line L, I have a point A. I want to construct a parallel line passing through A. So that's the idea. So this is essentially, I usually like, you can see my style now that I like to draw this kind of illustration picture, like to memorize that what we have done here. Okay, so I want to construct a parallel line passing through a given point, okay? So now again, you're going to see that unfortunately that this is another proposition that Euclid is going to use the older proposition. So I'm going to actually do 2 ways. So first, I'm going to just go over quickly or essentially sketch what's the construction steps that Euclid did. I want to kind of follow the original proof at least so we can see what's the philosophy behind. But of course, because it involves the previous construction, so I'm not going to have enough time to redo all the previous construction carefully. So the picture here you're going to see is just really a sketch here and maybe a little bit cheating here. But at least we can go over the construction steps and see how Euclid or they prove this construction, verify this construction. And since we probably still have a little bit time, I'm going to provide a alternative construction. And as I said, this is not, Euclid's construction is not the only construction. So it turns out that there will be other construction, maybe involve a couple more steps, but it doesn't necessarily need to quote another previous like construction. So that's why I think there's also a benefit that we can take a look at other construction here. Okay, so first let's go over how Euclid do this, right? So say we have a given point A and a line BC, right? So first thing what I'm going to do is that I'm going to pick some random point D here on BC, okay? And I'm going to join AD, okay? Now you can see that this is the cheating part come from, right? The sloppy part. So essentially the philosophy is again back to the previous proposition. Well, essentially you are using proposition 22. So what you want to do is you want to construct an angle. So you already have this angle DA, actually, yeah, so you already have this angle ADC, right? So that's coded, give a name, that's coded alpha here. Okay, so the idea is I want to be able to reproduce, and first let me draw a sketch here, reproduce an angle here that's coded DAE, such that this angle is going to be alpha, okay? And this is the steps that essentially we're quoting the previous proposition we just did, right? Previous proposition, we said that if you give me a line and give me an angle, I can reproduce the angle on this side, right? So this is exactly what we just did. And the essential concept is simply just reproduce another triangle, right? So let me just like quickly do a rough construction here so we can see what's going on. So let me just roughly draw the picture. I don't have time to draw a very rigorous one, but just bear with me. So let me see. So I need, okay. So I think I got the correct point here. Okay. I'm doing a cheating step, definitely. Please do not mimic me. I'm just need to do it quick, so I already omit a lot of steps here. So essentially, what I do, or what we want to do, is construct this angle DAE such that DAE is the same as ADC, okay? And if we have that, that's essentially the sloppy step 3 here. Then if we extend this line EA, then this line, I claim EA is going to be parallel to BC, okay? And you can see from the picture, this is exactly what we just did with proposition 1.27, right? So 1.27 tells us if you have equal alternate interior angles, then it implies two lines are parallel, right? So the verification exactly relies on the proposition 1.27. So let me do the verification quickly. So basically, we can say that since the line AD, which is crossing two lines, so it crosses let's call this EF and BC, right? And making alternate interior angle to be equal. So EAD and ADC are equal, right? Then I just said by proposition 1.27, these two lines are parallel. So you can see that we kind of keep going back to proposition 1.27. So now you can kind of see the importance of the statement, right? So I don't ask everyone to remember like exactly how to do the proof, but at least at this point, you should know how to apply the statement, right? Or essentially what statements we have here. Okay, so as I promised, I want to show you that there's another way to do it because I realized that this proposition is actually, the step is quite sloppy. So there's actually an alternative, a pretty nice way to do it. And it's not that hard at all. But of course, because I'm going to provide a different construction steps. So this means if you want to verify the construction, then the verification part will be different too, right? Because it's a different construction, even though we construct the same thing. So let's see. So again, we start with the outside point and a line BC. And this alternative construction tells us that what we can do is just take A as a center and draw any circle as long as it intersects the line BC. Okay. And that's called these two intersection points, Q and R. Okay. Now I construct another circle centered at Q with radius QA. Okay. And this intersect the line BC at S. Okay. Now do it again. You draw another circle centered at S with radius SQ, sorry. Okay. And now, let me highlight it. Where's my pen? So first, we already construct circle center at S with radius SQ, right? Now this circle we just draw here, it's going to intersect the first circle that we draw center at 8, right? At a point T. Okay. And now the line AT is the line we want. Okay, sorry, I was not drawing very carefully, but roughly you can see that's the case, right? So you can see that line AT is the design line. So in some sense, you can see this construction is better, right? And you don't need to use the previous proposition. So if you really just search online, you can see a lot of this kind of different construction with different type of flavor. So what I'm going to do is that I would leave you to figure out that what's the verification here, because actually this is actually nice challenging. You can see that all I really did here is construct a lot of circle. So with a lot of circle, you're going to have a lot of equal sides, and with a lot of equal sides, I can see that probably the proof is going to use like maybe proposition 1.27 again, right? So in some sense, probably you can create, because you have all the equal sides, you can probably create some equal angles, and then you're going to use the proposition 1.27 again. So you can think about it. I think it's a nice challenge problem that I already give you the proposition, the construction. You can kind of see whether you can come out with the verification proof yourself. Okay, so this is actually a nice exercise, a little exercise. So I'm going to include this as part of the lecture as well, because I think this is a nice way that you have an alternative other than the original Euclid's way. Okay, so I don't think we have any time to start something new. So I'm just going to give you a heads up what I'm going to do next. So, so let me show you something. I want to stop sharing here. So actually, before I close this, does anyone have a question about the construction I just did here? Okay, so let's see. So I'm going to first turn off this so I can. Sorry, I pulled the wrong line. Okay, so let's see. Okay, so where's the share? Okay, so I want to share this. Okay, so as I mentioned that the last thing I want to do is essentially, actually, can everyone see the PDF, right? Okay, so now let's see. So the next thing I want to do is what we call the axiomatic system. Okay, so this is essentially what chapter 6 is doing. So that's why I really need everyone to read chapter 6 in advance. That, of course, I mean, I don't expect everyone to finish reading or fully understand it, but at least you should have some general understanding that what's going on for chapter 6. So what we're going to do is that if you still remember that back in the time when we introduced the definition or the axioms for Euclid, I mentioned that Euclid's axiomatic system is actually, there's a flaw, right? So if you think about it, back then we deferred the proof of SAS and SSS congruent scheme. And one of the reasons is that Euclid used this superpose type of proof, right? He said that he wanted to move a triangle onto the other one. This is something that he didn't justify. There's actually a lot of things that he didn't justify. For example, that there's few things that we keep using, but we kind of take it for granted is that, for example, two circle, it's going to intersect at 2 points or one of the point, right? How do you know this is true, right? This is not included in this axioms, right? So it turns out that Euclid's axiom is not complete in the sense that there's a flaw, right? So it turns out that in the late 19th century, early 20th, Hilbert, another great mathematician, he come out with a better improved axiomatic system. He also talked about in order to be a nice axiomatic system, your system need to satisfy certain property. This is exactly what you saw, like consistency, independence, and completeness. Okay, so we're going to talk about that, what's the necessary requirement for an axiomatic system to be good. And then we're going to talk about a lot of logic, that what's the example for having an independent axiomatic system. So it turns out Euclid's problem is because that his axiomatic system is not complete. Okay, that's where the problem is. So complete means that he did not include enough axioms. So he omits certain things that he didn't justify. Okay, that should be included with the axioms. Okay, so next, the coming Wednesday, I don't think I'm going to finish this slides. As you can see, there's a lot of information here. So I'm going to separate the slides presentation into 2 parts. So next Wednesday, we will do maybe the first half, and then this Wednesday, and then also coming back next Wednesday. Because I think next Monday, it's going to be Labor Day, so we don't have class next Monday. Okay, so I'm going to stop here. As I mentioned that I will stay for a couple minutes. So if you have any questions, you can let me know. Otherwise, you're free to go.
Yeah, can you just draw or help me draw 3.3 number 15?
Okay, so first let me readjust my window here because I actually messed it up. So now I cannot see the chat very easily. So, okay, let me see. Hold on, I have, oh, thank you, okay. Okay, so let me see, what's the question? So you want the picture, okay. And also, is clear now here? Are you still here?
Me?
Someone asked me about, is that clear now? Cleona, are you still here? You asked me, who is the one that asked me the question at the beginning about the same problem? 3.3. Yeah, okay. Oh, sorry, I didn't notice like who actually okay. Yeah, so I think there are 2 different people asked me the same question. Okay, so let me first let me pull out the homework questions. Give me a second. Okay, so so both of you have questions on number 15, section 3.3, is that correct?
Yes.
Okay, so let me see the textbook. I don't remember on top of my head. Okay, so let's see. So let me share a screen with the whiteboard. Okay, so whoever's still here should be able to see the whiteboard now.
I can see it.
Yeah. Okay, so with my pen. Yeah. Okay, so it says in triangle ABC, we'll assume AB is less than AC. Okay, so we want to draw an indication, just AB less than AC. Something like this. Let's just draw whatever triangle, as long as AB is less than AC, it's going to work, okay? And that D be the intersection of an angle bisector at B and C, okay? So angle bisector, so what angle B and C, okay? So I want roughly here, right? That's angle bisector. So this is, let's call it alpha and alpha, right? Because they're the same. And let me use another picture, another line. So I have another angle bisector here at C, right? B and C, okay? So now I also have this angle the same as this, right? And the intersection, what we want to call D. Okay, so what do they want? They want proof DB is less than DC. DB is less than DC. Okay, I mean, from the picture, it kind of tell you true, right? But the only information we really know is this, right? And what's the given? Given says AB less than AC.
Yeah, I wrote that down wrong. That's why my picture wasn't coming out right.
Yeah.
I had AB greater than AC.
Yeah. So I think so. Just be careful. You draw the correct picture. You need to use all the given correct assumption. Okay. So let me see. I need to recall. So I'm pretty sure this is we're going to use proposition 18 and 19, where within a triangle, the bigger angle is going to corresponding to the bigger opposite side. And vice versa. If you have a bigger side, it's going to give you the corresponding angle. And because of the construction, you also know that there's an angle bisector. So essentially you have alpha, alpha, beta, beta here. You're probably also going to need it as well. So do I need to do more, or that's enough of hint?
I figured out what I was doing wrong. You don't
Okay.
have to,
so
help more.
What about so the other person, now I'm confused who's talking. So are both of you okay now, or you need more? Give me a signal. Or anyone need more hint? So AB is less than AC. We can use that to prove DB is less than DC. Yeah. So okay, let me give you the first hint. So because AB is less than AC, right? So you can see the first step I can imagine is that in the triangle AB and C, because side AB is less than AC. So the first step I can imagine that you're going to get is to use, I forgot which one is which, you need to check yourself, one of the proposition, either 18 or 19, that, oops, what's happening here? Where's my, okay, where's my whiteboard? Okay, oh, here, sorry. Okay, so in triangle A, B, and C, you have AB, right? But AB is corresponding to angle C, right? So this angle C should also be smaller then the angle corresponding to AC. So that's essentially angle ABC, right? And what's ACB? This is 2 beta, and this is 2 alpha, right? So yeah, with the angles, yeah. So now you know angle 2 beta is less than 2 alpha. Then you can start from here, getting the relationship between beta and alpha, and then do the other way around to conclude the side you want. So it should be straightforward once you have the correct picture. And most of the time with this kind of proof-based theorem or proposition or statement, you need to use all the information you have here. So if you cannot prove it, that means there's some missing condition that you didn't use. Okay, so any other questions?
I think I'm good, but I'll probably stop in tomorrow for.
Yeah, definitely. Yeah. Think about it, because I kind of a little bit reluctant to tell you everything now, because I think once you kind of like, sometimes if you get stuck too long, put it aside. Come back later, you will have a fresh mind. I mean, this is how mathematicians do research. Anyone who do math problem, like sometimes you're in a blind spot, right? You're so into a specific problem for too long, so you kind of confused. So a lot of time, what I would do is just put it aside and come back maybe a couple hours later or the next day. Then you have a fresh mind, and then you can start over, and then it should be more clear. So if you still have any questions, please stop by tomorrow. And if you really cannot make it, send me an email in advance so we can set up a time, or maybe I can tell you the hints or something through the email.
Okay, thank you.
Yep. Any other questions? So I'm going to stop here.